To understand why this bridge failed, we have to go back, long before the day it collapsed. Back to a time when America was building at an extraordinary pace. When this bridge was first designed, the country was in the middle of an infrastructure boom. Cities were expanding. Traffic was increasing. Engineers were being asked to solve problems quickly and efficiently. Bridges were not just transportation tools. They were symbols of progress. This bridge was designed to meet the standards of its time. It followed accepted engineering practices. It was reviewed, approved, and constructed with confidence. And at the time, there was no reason to doubt those decisions. Because engineering, like all human systems, is shaped by the knowledge and assumptions available in that moment. The bridge used a structural system that was widely trusted. Steel components carried loads through interconnected elements. Forces were distributed across beams, joints, and plates. Nothing about the design appeared experimental or risky. In fact, it was considered efficient. Efficient designs use less material. They reduce costs. They meet performance requirements without excess. And for decades, this approach worked. But efficiency has a hidden weakness. It leaves less room for error. When people imagine bridges, they think of massive beams and towering supports. But bridges don't fail because of the biggest pieces. They fail because of the smallest ones. In this bridge, certain critical components were responsible for holding multiple structural elements together. They were not designed to bend. They were not designed to stretch. They were designed to hold. As long as those components performed their job, the entire system remained stable. But if even one of them became overloaded, the consequences would ripple outward. At the time of construction, engineers made assumptions that seemed reasonable. Traffic volumes would grow gradually. Vehicle weights would remain within expected limits. Future modifications would be modest. Those assumptions were documented, reviewed, and approved. And for many years, they appeared correct. Traffic increased, but not suddenly. Repairs were made, but within expected ranges. Nothing dramatic happened, and that lack of drama reinforced confidence. As the years passed, the bridge aged like all structures do. Steel expanded and contracted with temperature changes. Concrete experienced stress from repeated loads. Connections endured millions of cycles of use. None of this is unusual. Bridges are designed to age. What matters is how that aging is managed. Most Americans never see a bridge inspection. They don't know how often inspections occur. They don't read engineering reports. They don't study load ratings. And they don't need to, because inspections exist to remove that burden from the public. Inspectors examine visible components. They document wear, corrosion, and cracking. They rate structures using standardized systems. These ratings determine whether a bridge stays open, receives repairs, or is scheduled for replacement. In theory, this system works. In practice, it depends on interpretation. This is one of the most misunderstood terms in American infrastructure. A bridge labeled structurally deficient is not automatically unsafe. It means that certain components do not meet modern standards. Many bridges across the United States carry this label and remain open for years. This classification can create a dangerous illusion. The public hears deficient and assumes urgency. Officials hear deficient and see a familiar category. And when a condition becomes familiar, it becomes normalized. Over time, the bridge underwent modifications. New equipment was added. Safety features were updated. Traffic patterns changed. Each change seemed small. Each addition was approved individually. But bridges do not experience changes individually. They experience them collectively. Weight added in one decade remains there in the next. Stress accumulates. Margins shrink. And those margins are rarely visible from the surface. This bridge was designed under standards that no longer exist. Modern engineering places greater emphasis on redundancy. The idea that if one component fails, others can compensate. But this bridge did not have that luxury. Certain components carried more responsibility than engineers at the time fully understood. If those components failed, there was no backup. That is not a flaw by modern standards. It was simply how bridges were built then. Inspection reports noted issues: fatigue, stress, wear. But none of these findings triggered immediate closure. Why? Because they were not interpreted as imminent threats. Engineers often think in probabilities. A component may be overstressed, but not beyond failure. A crack may exist, but not yet critical. And when infrastructure budgets are limited, decisions become comparisons. Which bridge needs attention first? Which repair can wait another year? These are not careless decisions. They're constrained ones. To engineers, the bridge represented a set of calculations. To the public, it represented a promise. That gap matters, because when engineers see gradual deterioration, they see time. When the public sees an open bridge, they see safety. And as long as the bridge remains open, trust remains intact. One of the most important things to understand about this bridge is that there was no dramatic turning point. No report screamed danger. No inspection demanded immediate closure. Instead, there was a pattern: small concerns, manageable risks, deferred decisions. This pattern is common, and it is why infrastructure failures are so difficult to predict and so devastating when they occur. Engineering relies on models. Models rely on assumptions. Assumptions rely on data available at the time. What engineers did not know then is just as important as what they did know. Material behavior under long-term stress. The cumulative impact of repeated modifications. The interaction between multiple small changes. None of these were fully understood when the bridge was designed. From the outside, the bridge looked unchanged. From the inside, its stress profile was evolving. That difference is critical, because systems rarely announce when they are approaching their limits. They continue to function until they don't. This is the question Americans always ask. Why didn't someone stop it? The answer is uncomfortable. Because nothing appeared broken. There was no clear threshold crossed. No rule violated strongly enough to force action. And when responsibility is distributed across systems, agencies, and timelines, urgency becomes diluted. For decades, this bridge performed its function. It carried traffic. It supported commerce. It connected communities. It did not fail early. It failed late, after years of service, after countless successful crossings. And that success masked its vulnerability. The more familiar a system becomes, the less likely people are to question it. Inspectors see the same structure year after year. Officials review similar reports repeatedly. Commuters cross without a second thought. Familiarity creates comfort. Comfort reduces urgency. At no point were commuters told, "This bridge is aging. This design has limited redundancy. This structure carries less margin than modern bridges." They were never meant to be told, because the system was designed to manage risk quietly. And quiet systems fail quietly until they don't. By the time the public became aware of the bridge's vulnerabilities, it was already too late. The engineering story had been unfolding for years. Not dramatically, not urgently, but steadily. And that is what makes this failure so instructive. This bridge was not unique. It was representative, built during a period of rapid expansion, maintained under constrained budgets, modified incrementally. Thousands of bridges across the United States share similar histories. And that reality raises a question that engineers and policymakers still struggle with. How do you prioritize risk when failure is rare, but catastrophic? Engineering can predict stress. It can estimate fatigue, but it cannot always predict timing. Systems often fail not at the moment of highest risk, but at the moment of coincidence. A combination of factors, a convergence of conditions. That unpredictability is what makes infrastructure both resilient and fragile. The public saw a bridge. Engineers saw a system under evolving stress. Administrators saw budget constraints and timelines. Each perspective was incomplete, and none of them alone were enough to prevent what came next. This bridge did not collapse because it was ignored. It collapsed because it was understood, but not urgently enough. Because risk was acknowledged, but managed gradually. Because no single warning outweighed the comfort of continued operation. By the time the day of collapse arrived, The bridge was already operating closer to its limits than anyone realized. Not because of negligence, not because of recklessness, but because of accumulated decisions made in good faith. That is the most unsettling part of this story. In the next part, we move from design and history to the moment where knowledge met consequence, where warnings were no longer theoretical, and where decisions that once seemed reasonable became impossible to ignore. Because understanding how this bridge was built explains only half the story. The other half lies in what happened when people were told something wasn't quite right and chose to wait.